Okay, today we need to talk about the atomic spectrum of hydrogen as well as the Bohr atomic model. Two things that should be reviewed from Chem 1, but that we still want to make sure that we can cover. Okay, so if we think about hydrogen line emission spectrum, remember is that when the hydrogen line emission spectrum was being studied, most people thought that light behaved like a wave. And so what happened when we looked at the hydrogen line emission spectrum is that we found that light is emitted by excited hydrogen atoms when the bond is broken in the diatomic molecule. This is kind of the upper level version. Um, and what this whole idea of what we're going to talk about here, before we can really get into the excited atoms, we need to talk about the ground state of atoms and electrons versus the excited state. And really, an excited state is just when an atom has higher potential energy than it has at the ground state, and this is because we force it there. We use electricity, we light it on fire, but we do something. And for hydrogen line emission spectrum, we run electricity through it. Now, the line emission spectrum is a series of wavelengths of light created when the visible portion of light from excited atoms is shined through a prism. And we'll take a look at this at class, again, to remember. And scientists using classical theory expected atoms to be excited by whatever energy that was absorbed. They kind of expected this on the whole continuous spectrum. And the continuous spectrum is the idea of EM radiation. And they expected it contains all of the wavelengths of visible light. So they essentially expected to see the entire rainbow be given off by these atoms that were excited. And that wasn't what happened, okay? If you look at the setup of it, here's, excuse me, the regular white light source, and we'll look at this in class. When you look at the regular white light, you see the entire continuous spectrum, or GPIV. When we look at hydrogen gas and we look at it through a prism, we only see certain wavelengths and certain frequencies of light. We've got the orange band at 656 nanometers, pale blue at 486, darker blue 434, and then the violet at 410. So they were expecting to see this. This is what we actually saw. And so they had to kind of explain that because it didn't necessarily make sense. And why had hydrogen atoms only given off specific frequencies of light? Well, we got to come back to this whole quantum theory and their attempt to explain this with a new theory, the atom. Okay, and so we're going to back up a little bit and talk about Bohr here in a minute. Now, for the hydrogen line emission spectrum, maybe. There we go. Remember, when an excited electron falls back down, it emits a photon of radiation. And that photon is equal to the difference in energy of the original and final states of the electron. And we're going to do a little bit more math with this. But the conclusion part is that since only certain frequencies are emitted, only certain energies are allowed for electrons in the atom. And again, if we think about this, if this is n equals 1, n equals 2, so if the electron is excited, okay, and it doesn't want to be excited. Remember, it wants to have low energy. It's going to come back down, it's going to give off a photon, and that photon, the energy of the photon is equal to the difference between n equals 1 and n equals 2. And again, we're going to do a little bit more math with that this year. Okay, and then so secondly, we got to talk about the Bohr atomic model. Now, for the Bohr atomic model, it was created by Niels Bohr. He came around 1913, a few years after Rutherford in 1911. And he started to develop the quantum model. And actually, a lot of times we refer to the Bohr model as the planetary model because he incorporated the idea of quantums in terms of packets of energy, but he used a planetary system. So he developed a quantum model for the hydrogen atom that essentially explained the emission line spectrum. And he made some leaps on some things. It was certainly a step in the right direction. And essentially what he said is that the electron can only circle the nucleus in certain orbits, and those particular orbits all have certain amounts of energy. So again, it's this whole, if there's our nucleus, n equals 1, n equals 2, n equals 3 type of deal. And that's where we refer to it as the planetary model. Now, to continue with that, he had to create an accurate model. He had to use quantum theory instead of classical wave theory. So what that meant is he generated an equation to calculate the energy levels available to electrons in certain atom. We kind of left this out last year in Chem 1. Here's the lovely equation. We'll point out how we're going to use this in class. But n is an integer, z is the atomic number, okay, and this is really our principal quantum energy level of certain things. The negative sign makes the energy more negative the closer it is to the nucleus. So that's just a frame of reference type of thing. So the closer it is to the nucleus, the more negative that number is going to be. Now with the Bohr model, electrons can gain energy by moving to a higher energy level. They lose energy by coming back down. So again, if we have an electron, it's floating around here in n equals 1, and it absorbs energy, and it goes up to, let's say n equals 5. Okay, well, it doesn't want to be there. So if it's traveling around, and it decides, nope, I don't want to be here anymore. So it comes back down. It's going to give off a wavelength of light that's equal to the distance between n equals 5 and n equals 1. So in order to go up energy level, it's got to absorb. In order to come back down, it's got to give it off, which we saw last year as well. Now the photon that's released, again, has an energy equal to the difference between the initial and final orbit. So that's just showing you the same thing. If here's my electron path again, it gets excited. Let's say it gets excited from n equals 1 to n equals 3. It doesn't want to be there anymore, but it only drops down to level 2. It doesn't have to go all the way back down. It's going to give off a light that's equal to the energy that's between the difference between energy level 3 and energy level 2. So again, just another way to see that. Now, we also can use the equation to find the change in E when an electron actually moves energy levels. Okay, so we expand this a little bit where we've got the atomic number and we've got the energy level, the atomic number, and the energy level. Okay, so if we look at hydrogen, if we're dealing with hydrogen atom, that's why this number is 1 up here. And then we've got the difference between energy levels. And we'll do some of those math problems to see what that looks like. Now, continuing in that idea, the Bohr model, we can also calculate the wavelength of the photon using de Broglie's equation. Okay, or where we've got our wavelength, we've got our Planck's constant. Actually, this is not de Broglie's equation, it's a slight variation on it. But we've got, again, our we're looking for the wavelength. We've got Planck's constant, we've got the speed of light, and we've got delta E. Delta E is equal to 0 at a set distance, of infinity away, becomes more and more negative as the electron comes closer to the nucleus. Okay, a little heady, but again, I think we do at least one of these together to show you what that looks like in terms of practicality's sake. Okay, here were the problems with the Bohr model. Problems were that it did not work for other atoms besides hydrogen, and it did not explain chemical behavior. It didn't explain how or why things bonded together, which was a problem. Okay, now, again, here's some of the sample problems. This is on page 301, but if it wants to calculate the energy required to move the hydrogen electron from n equals 1 to n equals 2, then we want to also find the wavelength. So, remember, n final minus n initial. Okay, so we're looking for the energy required to move it. So that's why we've got 2 as the final and 1 as the initial. Everything else is given to us in the equation. And then we can take that, we get our energy, and we plug it in down here to find the wavelength. We find that it's 121.6 nanometers. And typically when we talk about visible light, we almost always talk about it in nanometers. So that's why we do that conversion and we don't leave it as meters. Okay, one other sample, calculate the energy required to remove the electron from the hydrogen atom in its ground state. So if we wanted to completely remove it, okay, we're going to end up with 2.178 times 10 to the negative 18th. Energy was absorbed by the electron, so the value for delta E is going to be positive. Okay, a little bit of that endo-exothermic because we've missed it so much. Okay, and then flame tests. These are colors that are commonly asked on the multiple choice section of the AP exam. When Chem 1 runs the flame test lab here in a few weeks, we'll get to see, we'll just burn them to see what colors they burn. This is the factoid sheet I actually gave you at the beginning of last quarter. It's also on the website, but these are just like colors and solutions, some properties we should know of different substances. Okay, I hope that helps. Have a great